This is Lab 5, Faraday's Law. Alright, so as always, some quick introduction and some review of the concepts that we're going to be using in this lab. So the objective is to explore and observe how a magnet behaves when it is placed in a conductive tube. In this case, it'll be an aluminum foil tube. And then we'll compute a computational model to compare the experiment and the computational results. So some of the concepts that we're using are things we've been seeing over the past weeks. So Faraday's Law, which describes the proportionality between the magnetic flux and the induced IMF. We got Lenz's Law, which describes the flow of the current. We'll oppose the change in flux. And then we got the magnetic force on the wire in the formula there, which describes the force imposed when a current is flowing through a wire. Alright, so basically a little rundown about the experimental procedure. So we're gonna find the north pole on the magnet. So the north pole is a pole that repels, so that is easy to find. And then we place the magnet above the tube of foil, use a camera to record the starting and ending times of the magnet falling, and then we repeat a couple times and record the results. So as you can see on the image right there, this is basically upside down, so the magnet in this picture is going up, but in the experiment we'll be dropping it, so it'll be going down. And what we should expect is that the magnet will slow down due to the magnetic field produced by the aluminum foil, which is induced by the magnet. So we also built a computational model code, and here are the results. So the whole code, if you want to see it, will be linked in the bio. But the key takeaways from the code are that the acceleration decreases as the magnets get closer to the field. So let's just actually take a look at the graph right here. So you can see that the velocity is increasing rapidly, and then it increases and stays constant and then decreases again. So basically we can represent this when it is rapidly increasing as having an acceleration, and this is due to gravity. And then that acceleration will become constant, so the velocity is constant, and this is the time that the magnet is actually passing through the loop. And as the magnet passes through the loop, the acceleration caused to gravity will get greater because the acceleration due to the loop will become less, and thus, as you can see, the velocity starts increasing again. So if we compare these results, basically, from what I recorded, the real world experiment average time was about 1.4 seconds, and the computational model was about 1.2 seconds. So a little bit of a difference there, but when you think of it, that is milliseconds. And some observations is that if we flip the magnet around, we would have opposite signs for the current, and so the induced current would be clockwise instead of counterclockwise, because currently the induced current is counterclockwise. And then this is due to Lenz's law. And then the computational model and real world experiment are very close. The main difference is probably from human error and just error assistance and etc. But also, what's it called? It's just because it's a very tiny error. So some conclusion questions and some questions to think about. Basically, what if the resistivity of the conductor was reduced as close to zero? Like, so what if the resistivity is basically zero? How would the dynamics of the falling magnet change? Well, if there's no resistance, then the current is going to be at its maximum, theoretically infinity, but obviously, it'll just be at its maximum value, and therefore the magnetic field would be very strong, and the magnet would take a longer time to fall. So what if there are holes or slots cut into the tube? How would this affect the ring currents in your model? So if there were holes, holes or slots, there's going to be less surface area. And when there's less area, there will be less magnetic force on the magnet. And if there's less magnetic force on the magnet, then the magnet will fall faster. So that is the Faraday's Law lab, and thank you for listening.